Good morning, students. Can you all see my screen?
Yes, madam.
Yes, madam.
Right. So I think you can remember what we were discussing about the regression analysis. We were fitting the simple linear regression models, and then we discuss how to obtain confidence intervals for the parameters in regression line, right? So in the last example that we discussed, when you are fitted, when you are given with the data set, we know how to find beta naught and beta 1, and then we know how to estimate a value for y for a given value of x. So when it comes to regression, one of the main purposes why we are fitting regression lines is for prediction. We can forecast future values using our fitted line. So when it comes to prediction, there are two ways that we can predict. Using the fitted regression line, you can predict the mean value of y, that is the mean value of your response variable for a given value of x. Right? For an example, if x is equal to x naught, we can predict the mean value of y. And also we can predict the individual value of your response variable for a given value of x. For an example, when x is equal to x naught, we can predict an individual value of your response variable y. So let's first discuss the prediction of the mean value of y for a given value of x. So far we have discussed when it comes to this regression model, the model that we are fitting is this one. Yi equal beta naught plus beta 1 xi plus the random error epsilon I. And we have already proved that the least square unbiased estimators for beta naught and beta 1, that is beta 1 hat and beta naught hat, we can obtain them using these two equations, right? So if you take the estimated value of y, which is denoted by yi hat, we know the estimated value is equal to beta naught hat plus beta 1 hat xi. So if you can remember, when we were calculating the yi hats, we know we didn't consider the error term, right? Because as for the assumptions of the simple linear regression, the expected value of the error terms, they are approximately equal to 0. So because of that, when it comes to the fitted line, we know yi hat is equal to beta naught hat plus beta 1 hat into xi. So if you take this fitted line, the equation of this fitted line, uh, we can take the expected value of this equation, right? So if you take the expected value of yi hat, you have to take the expected value of the term which is in your right hand side. So that is, you have to take the expected value of this term, right? That is, you have to take the expected value of beta naught hat plus beta 1 into x. So when you take the expected value, right, you can see when you take the expected value, beta naught hat, it's a constant. So you can take the expected value of beta naught hat plus expected value of beta 1 hat into xi. So since beta naught and beta 1 are constant, when we know when you take the expected value, it's equal to beta naught plus and we know beta naught hat and beta 1 hat, they are the estimators, and we have already proved these are unbiased estimators. That is, when you take the expected value of these estimators, they are equal to the parameter value, right? That is expected value of beta naught hat, that is equal to beta naught. We have already proved that. So you can replace expected value of beta naught hat by beta naught, and expected value of beta 1 hat by beta 1 into xi. So we can see when you take the expected value of yi hat, That is, in other words, that is the mean of your yi. So that is equal to beta naught plus beta 1 times xi. So that is for a given value of x, right? The mean value of yi you can predict using this equation. So if you take, we can see when you take the expected value of beta naught plus beta naught hat plus beta 1 hat into xi, this term, it is equal to the expected value is beta naught plus beta 1 xi. So that is beta naught hat plus beta 1 hat xi is an unbiased estimator for beta naught plus beta 1 xi. අපි beta naught hat plus beta 1 hat xi කියන මේ term එක expected value එක ගත්තාම එයා ඔයගොල්ලන්ට පේනමැති සමාන වෙනවා එයාගේ parameter values වලට beta naught plus beta 1 xi. ඒ කියන්නේ එක unbiased estimator එක. So we can see we already know that beta naught hat and beta 1 hat, they are also unbiased estimators for beta naught and beta 1. So in this case, we can also see beta naught hat plus beta 1 hat xi. This whole term is an unbiased estimator for beta naught plus beta 1 xi. So when it comes to the confidence intervals, we can actually prove if you take the variance of this yi hat, right? We can prove that variance is equal to sigma squared into 1 over n plus xi minus x naught squared over sxx, right? This term we can prove, and we'll be discussing that under assignment 2 because I hope last week you didn't discuss. I asked the demonstrators not to discuss this part. So in the next coming up assignment, we'll be discussing about this variance. And now if you take this, if you take beta naught hat plus beta 1 hat xi, this term. Now we know the expected value. In other words, its mean is beta naught plus beta 1 times xi. And this is the variance term. So if you know the mean and the variance, we can convert that into a standard normal distribution. So you take beta naught hat plus beta 1 hat into xi, this term, and you have to subtract its mean value, which is equal to beta naught plus beta 1 xi. So that is why if you look at this one, in the numerator, you have beta naught hat plus beta 1 hat into x. That's the term that we are interested about. And from this one, we are going to subtract beta naught plus beta 1 x. That's the mean value. And you have to divide this by the standard deviation. So this is the variance. And you have to take the standard deviation. And now this is having a standard normal distribution, right? And also we can prove, we know a known distribution, that is if you take if you take n minus 2 into sigma squared hat over sigma squared, this term is having a chi-square distribution. This is a known distribution. That is, if you take any estimator of variance and if you divide it by the variance parameter, and then if you multiply this by a particular degrees of freedom, this quantity is having a chi-square distribution of that respective, with that respective number of degrees of freedom. So in this case, we have considered n minus 2. So that in this case, this quantity is having a chi-square distribution with degrees of freedom n minus 2. So here we have a standard normal distribution, and here we have a chi-square distribution. Now what we are going to do is, if you have a standard normal distribution and chi-square distribution, we can again form a t distribution. How we are going to form? So using the theory, if you just divide the standard normal distribution with the chi-square, with the square root of chi-square distribution divided by its degrees of freedom, then it's having a t distribution. We can convert that into a t distribution with with that respective number of degrees of freedom. So in this case, you can see the degrees of freedom, that is n minus 2. So what you have to do is now Z is this quantity, that is beta naught hat plus beta 1 hat into x minus beta naught plus beta 1 x divided by this variance term. So you have to take that one, and then you have to divide this by the chi-square distribution. So the chi-square distribution is this. So again, you have n minus 2 into sigma squared hat divide by sigma square, and the chi-square distribution, again you can see you have to divide by the degrees of freedoms, right? So in this case, you can, the mu value, the degrees of freedom is n minus 2, so you can substitute n minus 2 here. So when you substitute n minus 2, that will cancel out, right? So then you can convert this distribution into a T distribution where the degrees of freedom is equal to n minus 2. Now, if you look at this term, right, so we can see we have, in this case, if we want to find out a value, if we want to estimate a confidence interval for yi, so we know yi is equal beta naught plus beta 1 x. So when x is equal to a particular value, let's say x naught, you can substitute x naught here for x, then you can obtain a confidence interval for y. Right? So you can, when you obtain a confidence interval, you will get this equation to find out a confidence interval using this test statistic. And in this case, if you take the width of this confidence interval, so the width is given by, that is the difference between these two values. So the width is given by this equation. So this is the variance term into the test, into the table value of the T distribution, right? And then if you look at this one, you can see, if you look at this confidence interval, if you look at the equation of the confidence interval, you can see here, you have x bar minus x naught. So when this x bar is equal to x naught, this whole term will become 0, right? So that is, you have the minimum width value of this quantity of this confidence interval when x bar is equal to x naught, right? That in that case, you can obtain the minimum width value. So that is when you're given with the regression line, after fitting your regression, how to forecast or how to predict for the mean value of y, right? So in this case, if you just consider an individual value of y, how to forecast for an individual value of y for a given value of x. For an example, now our fitted regression is yi equal beta naught plus beta 1 xi into epsilon I. Now let's imagine now when x is equal to x naught, we want to find out the value of y. So we saw when you take the fitted regression yi hat, that is equal to beta naught hat plus beta 1 hat into xi. In that case, we saw when you take the expected value, that is again equal to beta naught plus beta naught hat plus, so beta naught plus beta 1 x, right? So in that case, we know when you take the expected value of yi hat, that is not equal to yi. So that is when you forecast or when you predict the value for an individual value of y, it's not an unbiased estimator for y. Because when you take the expected value, it's not equal to y. So, but what we can do is when we want to predict the value, what we can easily do is we can substitute the corresponding value of x to the equation as we did last week and find the value of y for a given value of x. Okay. So in this case also, we can find a confidence interval. Now, we can see here now, as I told you, the expected value is not equal to yi, right? So yi hat is equal to this equation. So since it's not an unbiased estimator, we have to find the variance in this case. Okay, so variance, we can, how we are going to find the variance in this case is, we know if you have a random variable x, variance is equal to expected value of x squared minus you have to subtract the squared value of the expected value of x. So using this general equation, we can show if you take the variance of this quantity, that is when you are predicting a single value, that is equal to this one, right? So the proof we'll be discussing in assignment 2 again. So using this one, now you know the expected value, that is beta, if you take the expected value of this, that is beta naught plus beta 1 x, right? And then x naught. So then we can, for a particular value of x, right? And then this is the variance. So then we can convert this into standard normal distribution, right? And as we discussed earlier, since we know the variance term, we can just obtain a chi-square distribution. So using that, we can obtain the t distribution by taking the ratio. And then just as we discussed earlier, we can form this confidence interval, right? So this is a confidence interval to obtain, this is a confidence interval for y for a given value of x, right? So with that, we are going to finish talking about confidence interval in simple linear regression. And then right. So as what we have discussed so far is, now when you're given with the data set, uh, you know, by taking the mean value and by subtracting the mean, how to find out by substituting the values to the equation, how to find out beta naught and beta 1, and to how to find the regression equation. Now, when it comes to any regression model, we can also present the regression model using matrix form. So in this case, if you look at this one, now here, since we are interested about the simple linear regression, so that is yi equal beta naught plus beta 1 xi plus epsilon I. In this case, we are going to first talk about how to write the simple linear regression in matrix form, right? So we have two variables, that is x and y. So if you take, now let's imagine, as for the general format, now let's imagine in our data set, we have n number of pairs, right? N can be any value. Let's say n is 8, n is 10. Likewise, we have n number of pairs. So if you have your data set with n number of pairs, for an example, in the example that we discussed in last week, we have the training times and the time that each employee is taken to complete a given task, right? So in that case, you have number of pairs. So you have, let's say we had 8 number of pairs. So you have 8 y values and you have 8 x values. So imagine you have n number of y values. So if you take your y variable, we can take it into a matrix, right? So it's actually, you have only one column with n number of rows. So this is a column vector. So y1, y2, likewise, you can place up to yn, all the y values into one matrix, one column matrix. That is the matrix of the random variable y. right? So you can see, since we have n number of values, so you have n rows and one column. So the dimensions, you can see this is a n into 1 matrix, right? And if you look at the error term, now since we have n number of pairs, for each pair we can talk about the error. So in that case, we need to have again n number of error terms. So that is, we have epsilon 1, epsilon 2 up to epsilon n. Again, that has n number of rows but one column. So you can place all your errors into one matrix like this. So this is your error matrix. And when it comes to simple linear regression models, so far we saw when we fitted the regression line, we are always estimating only two parameters, the intercept and the slope, that is beta naught and beta 1. So when you place the two parameters into another matrix, we denote that as the matrix of beta. So you have only two parameters, beta naught and beta 1. So since you have two parameters, you have two rows. So it's a 2 into 1 matrix. Now we know here, for each value you need to have, now if you look at your left hand side, it's a n into 1 matrix. So if your left hand side is equal to your right hand side, so your right hand side should also add up to n into 1 matrix, right? But here you have epsilon is n into 1 matrix, right? But beta naught plus beta 1 x1, this term you have to convert into n into 1 matrix. Now we have our random variable x. For x also we have n number of pairs, that is x1 up to xn. But since we want to calculate this beta naught plus beta 1 xn, so that is each x value you have to multiply by beta 1 plus beta naught. This is what we have to do. So you take first x value, you have to multiply this by x1 plus you have to add beta naught for this one. So since we are going to add beta naught for each and every x value, so we are going to add a column to the x matrix x, that is we are going to replace column 1 with ones. That is when you multiply 1 by beta naught, you will get beta naught as the constant. And then the second column is your x variables, right? So now you have two columns here and you have n number of pairs. So that is, this is a n into 2 matrix, right? So when you multiply this n into 2 matrix with 2 into 1 matrix, you can see again, now you will, here you have n into 2 matrix, right? You have n into 2 matrix, and then this one you have to multiply by n 2 into 1 matrix, right? So in this case, what will happen? When you take the product of these matrices, that will add up to n into 1 matrix, right? So that's what we are going to do. So you take your x, matrix x as this. The first column you have to replace by ones, and for the second column you have to put all the values of your x variable, and then you will have your matrix x. Okay, so then when we write these matrices, we have a matrix for our random variable y, for our random variable x, for the parameters beta naught and beta 1, and for the random errors. And then we can write down the matrix to denote the matrix form of the simple linear regression model, that is y equal, matrix y is equal to product of matrix x into matrix beta plus epsilon, right? And in this case, we know if you just take the expected value of the fitted regression line, we have already proved when you take the expected value of y, that is equal to beta naught plus beta 1 xi. Why? When you take the expected value of y, that is when you take the expected value of the term which is on your right hand side of this equation. So beta naught is a constant, beta 1 is a constant, right? So you have beta naught plus beta 1 x, and when you take the expected value of epsilon, that is equal to 0 as per the assumption. So when you take the expected value, you get this equation. So you can see the expected value is beta naught plus beta 1 xi. So if you want to get this term, what you have to do is you have to take the product of matrix x and matrix beta. So when it comes to the matrix form, to take the expected value of y, what you have to do is you have to take the product of matrix x and matrix beta, right? So we know in the assumptions of the regression model, when you take the expected value of this epsilon or the random errors, that is equal to 0. So in the matrix form also it's the same. If you take the expected value of this epsilon, that should be equal to 0. And if you take it as a matrix, you will see that is a column vector which has n number of zeros with one column. And if you take the variance of this matrix epsilon, you will see again that is you have that is a variance is a constant, let's say sigma squared, right? So in this case, but what we discussed was when you fitted the regression line, when we want to find the parameter, when we want to find the estimate values for the parameters beta naught and beta 1, what we did was we took the regression line and then we take the squared values of the errors, and using the least square method, we wanted to minimize the squared summation of the errors as much as possible. So the same thing we are going to do when it comes to the matrix form. So to take the square terms of the errors, that is in other words epsilon squared, let's take it as omega. So when it comes to the square terms of the matrices, we can take it as the transpose of the epsilon into the the same matrix. And this is our model, ye matrix y is equal to matrix x into beta plus matrix epsilon. And if you just write the error term, if you are using this equation, that is matrix y minus matrix x into matrix B. Since we are interested about the squared value, that is we are taking the squared means in matrices, the transpose into the same matrix is equal to, you have to take the transpose of y minus x into beta into y minus x beta. So we can, if you just solve this metric, this one, right, we want to find out the estimated value for beta naught and beta 1, we will see now what we have to do is, this is the equation for the squared summation of the squared errors. Now we have to minimize this, so that is this equation you have to differentiate with respect to beta. So in that case, we will see if you, since the parameters are beta, if you differentiate this with respect to beta, beta is equal to x transpose into x inverse x transpose into y, right? So when it comes to the matrix form, you can use this equation in order to identify or in order to estimate the given parameters. So in your examination, if I give you the data set and then I ask you to fit the regression model, you can use any method. That is, you can just take the least square estimator equations and substitute the values and find beta naught and beta 1. Or if you like to do the calculations using the matrix form, you can use this form, this method as well, right? Let's discuss this example, then you will you will understand how to use this matrix form, right? So you can see, find the most suitable regression line for the given data using matrix notation. So this is our data set. You have a number of y values and number of x values. Here we want to fit the regression line. Now let's use this matrix notation to fit the regression line, right? So in your examination, you can use your calculators to find the inverse and to find the product of the matrices, right? Since it's easy to explain using the Excel, right? I'm going to use Excel for the calculations, right? So this is our data set. We have 10 number of y values and 10 number of x values. Okay, so what is our result? What we have obtained? This is the result. That is, we know beta, the parameters, the estimators of the parameters we can obtain using this equation in matrix form. So if you look at this equation, you can see you have x transpose into x, and then you have to calculate the inverse. Then you have x transpose y, then you have to take the product of these two. Right, so as we discuss, now when you take the matrix X, so here for X you have 10 values, right? Starting from 35.3 to 57.5. So as I explained you, when you take the matrix X, you put all these given values into your second column, and the first column you have to replace by ones. So since you have 10 number of observations here, you have to replace the first column by 10 ones. So this is your matrix X. අපි ඉස්සෙල්ලාම කරන්නේ matrix X එක ලියා ගන්නවා. ඕගොල්ලන්ගේ data set එකේ දීලා තියෙන X values ඒ ටිකම අපි අරගෙන second column එක විදිහට දා ගන්නවා X කියන matrix එකේ. හැබැයි ආගේ first column එක වෙන්නේ අපිට data points 10ක් තියෙන හින්දා එකේව 10යි. So this is your X matrix. And now we have to take the transpose of X if you look at the equation. So transpose means you take the first column, that is you have 10 ones, you can write it as the first row in the transpose. And you can take the second column, you can write that as the second row in the transpose. So you can see I have the matrix X and I have the transpose of matrix X. Okay. So what I'm going to do is I have matrix X and I have the transpose of matrix X. So if you look at the matrix X, here you have 10 number of rows and 2 columns. So in other words, this is 10 into 2 matrix, right? And if you look at X transpose, there you have only 2 columns and 2 rows and 10 columns. So that is, this is 2 into 10 matrix. Now we are going to take the product of these 2 matrices, right? We are going to take the product of X transpose into X. That is, we are going to take the product of a matrix X transpose. The dimensions are this, that is 2 into 10, and the matrix X, the dimensions are 10 into 2. So we are going to take the product of these 2 matrices. So you can see when you take the product of these 2, right? When you take the product of these 2, so that should give you a matrix with dimensions 2 into 2. Right? So since it's easy for me in Excel, I can directly calculate the product. So I hope you know how to calculate how to do the matrix calculations using your scientific calculators. If you don't know, I know you have already learned when you are learning mathematics in your first year and second year, but if you have forgotten, it's high time to just have a look. And if you have forgotten, you can ask from a friend and just refresh your knowledge, right? So in this case, now I'm going to take the product. You can see it's a 2 into 2 matrix. So that is X transpose into X. So in Excel, if you want to calculate the product of two matrices, what you have to do is first you have to check the dimensions, the results. Now we can see in the result, you will have the matrix with 2 rows and 2 columns. So here you have to select 2 rows and 2 columns, and then you have to go to the function bar and you have to write equal. Since I'm going to multiply 2 matrices, the function is m mult. See, when you press M, you'll get matrix multiplication. You have to select this function. And what is our first matrix? That is the X transpose. So I'm going to select X transpose matrix here. So, and comma, then you have to select the second matrix is X. I'm going to select the matrix X here, and then I'm going to close the brackets. And here, then you have to press Control, Shift, and Enter together to obtain the 4 values, right? So I'm just telling you, because when you go to the industry, in most of the companies, they are using Excel. So if you have a good knowledge in Excel, that will help you, especially when you go for your intern, right? For the general students also, when you go to the industry, that will be useful for you. So this is how you obtain the product of this X transpose and X using this these two matrices. Now here we have to take the inverse of this. Now we know the values of X transpose X. Let me copy this into this sheet. So I will just paste here. So these are the values of X transpose X. But we are interested of finding the inverse of this, right? Since this is a 2 into 2 matrix, we can just manually calculate the inverse also, right? So in this case, so we are not going to discuss those, since you have discussed how to do the matrix calculations in linear algebra. And in this case, I will show you how to take the inverse using Excel. In the exam, you can use your calculator, or you can do the manual calculation as well. So we know when you have to obtain the inverse of a given matrix. Now this matrix X transpose X, it has 2 rows and 2 columns. This is a 2 into 2 matrix. So inverse will also have 2 into 2, the same dimensions. So you can select 2 rows and 2 columns, go to function bar, equal. So we are going to calculate the inverse of the matrix. Then you can press M inverse. This is the function matrix inverse. Then you can select the matrix that you want to calculate the inverse, close the brackets. Then you have to press Control, Shift, and Enter. Then you will get the X transpose X values, right? And now we have calculated X transpose inverse of X transpose X. Now we can calculate this one, X transpose Y. Right? When you take X transpose Y matrix, so this is our X transpose, right? And this is our Y matrix. Now let's calculate, if you look at matrix Y, you have 10 rows and 1 column. That is a 10 into 1 matrix. And if you take X transpose, that is you have 2 rows and 10 columns. That is 2 into 10 matrix. So when you take X transpose into Y, that is you have 2 into 10 matrix and Y is 10 into 1. So when you take the product, you will get 2 into 1 matrix. So we are going to take X transpose Y, that is 2 into 1 matrix. So I'm going to select 2 rows and 1 columns, and equal, I'm going to take the product matrix multiplication. X transpose is the first matrix that I have to enter, and the second matrix is matrix Y, and Control Shift Enter, you'll get X transpose Y. So in our previous calculations, we have obtained X transpose, inverse of X transpose X. So I'm going to copy it here. So here X transpose Y, this matrix is 2 into 1, 2 rows and 1 column. And then here you have 2 into 2. So if you can remember, when you look at the equation, now you have to take the X transpose X inverse and multiply that by X transpose Y. Now we have individually, separately calculated these two matrices. That is, we know X transpose Y and the inverse of X transpose X. Now we have to take the multiplication, the product between these two, to calculate the, to find out the estimators for the parameters using the matrix form. So in the last calculation, that is, you have to take the product of this and product of this. So that is, you have to take the product of X transpose X inverse is 2 into 2 matrix, and X transpose Y, that is 2 into 1 matrix. So you can see when you take the product, you have to get 2 into 1 matrix. So what I'm going to do is, I'm going to select 2 into 1 matrix. And in the function bar, matrix multiplication, my first matrix is X transpose X inverse. I'm going to select that. And the second matrix is X transpose Y. I'm going to select that, close the brackets, Control Shift Enter. Right? So you can see you will get two values. So this is these are the two values. These are the estimators of your parameters. This is the matrix. This is the matrix beta, right? So you can just see we get two values. That is, the two values means the first value, that is the value of the intercept, and the second value is the value of the slope. So in this case also, we can just come up with our fitted regression model, right? So that is Y is equal to slope is this one. Right, slope is this one. And then we have slope times X. And then we have slope times X plus our intercept value is, intercept is 14.40937. So in this case, this is our regression model, right? Or you can just write it in the other way around. That is, Y is equal to 14.40937. Since the slope is minus, you can put minus sign here. Minus 0.09127 times X. So this is the fitted regression model using the data set, and here we use the matrix notation. So you can just check today after the lecture, you can take the same data set and you can just use the least square equations and just solve this manually, and you can see whether you get the same result. Same values for beta naught and beta 1. So in this case, beta naught is 14.4 and beta 1 is minus 0.09. So you can do the same, you can obtain the same values using matrix notation, or if you do the calculations using least square regression equations, right? So is that clear for y'all? Do you all have any questions up to that point? Do you understand how to calculate the estimators using the matrix notation?
Yes, ma'am.
I know it's not like that we are doing lectures physically. So if you if we were having all these lectures physically, we can nicely explain all these calculations on board. So I know it's hard sometimes for some people. I know it's hard to catch, but you can, since I'm uploading the recording, you can just when you have a free time, go through again with the recording. And if you have any question, um, even if you don't have questions now, you will get questions later, so you can always ask your questions, right? You can just send an email or you can send me a message. Okay, so don't hesitate. If you have questions, you can have to clear everything when you move to the next session. So please go through all these recordings again and again, then that will help you. Okay, with that, right. So we can, what we can now here, we calculated using the matrix form, our fitted regression line using the matrix notation. So at the same time, we can show if you take the expected value of our parameters, expected value that is given by our expected value of beta hat, it's given by the matrix beta. So the matrix beta is the one that we have calculated so far. And then if you take the variance of beta hat, it is given by this equation, right? So that is, if you have the variance, if you have the variance matrix and then you have to multiply x transpose into x, we took the inverse of this one, then you have to multiply that using the variance matrix to get the variance of beta hat, right? And then okay, so these are the properties that we discussed. So if you take the expected value of these parameters, they are equal to beta. That is, when you take the expected value of beta naught, we know that is equal to beta naught. When you take the expected value of beta 1, that is equal to beta 1. That's why we call them as unbiased estimators. So no matter what is the method that you are going to use, whether it's the matrix notation or not, they are unbiased estimators. And also the variance is equal to sigma squared times x transpose x inverse. Okay, so when it comes to this regression, the simple linear regression that we are discussing here, there is an alternative form for the simple linear regression. So that is when you take the simple linear regression, that is yi equal to beta naught plus beta 1 xi epsilon I. So we can rewrite our regression equation like this. So what we are going to do is, we are going to replace our random variable here xi by xi minus x bar. So what will happen if I replace that by xi minus x bar? So you have yi equal to beta naught plus beta 1 times xi. minus beta 1 into x bar. So you have minus beta 1 into x bar term in this equation, which was not there in the original equation. So what you have to do is you have to add the same term to this equation to keep it as in the original equation. So you can see I have added beta 1 x bar term to the equation, and then you have the error, right? The original equation was yi equal beta naught plus beta 1 xi into epsilon I. So we replaced xi by xi minus I bar, right? So you can see when you replace x by xi minus I bar, when you simplify the brackets, you have beta 1 times xi minus beta 1 times x bar. So minus beta 1 times x bar, we have to remove from the model because that was not in the original model. So we can add beta 1 times x bar into this model plus epsilon. So if you rearrange these terms, since x bar is a constant, that is the mean value of this random variable, you can take beta 1 x bar and beta naught as one term. So we can denote this one by alpha naught, and then you have beta 1 times xi minus x bar plus epsilon. So you can see we have rearranged the model by replacing xi by xi minus x bar. We call this as the centered model of the a simple linear regression. So in some cases, it's important to fit this centered model because here what we have do is we have defined our the independent variable as the deviation from its own mean, right? Xi minus x bar, and sometimes this model is also important for some given data sets. So if you take this model, if you take, now here you have one parameter alpha naught and another parameter beta 1. So we can prove that if you check the estimated value for alpha naught hat, that is equal to the mean value of y bar. And then if you take the beta 1 hat, again you have the same equation to take beta 1 hat, and the variance you can prove by using these equations, the variance of alpha naught hat and beta 1 hat. These are the equations for the variance, right? So that we be discussing in assignment 3. So so up to this point, do you all have any questions? So since the cal is not working properly these days, and I think we have we discussed so many theory today, and also up to this point assignment 3 you have so many theories to discuss. So we'll do like this. The next one that we have to discuss is ANOVA. So before ANOVA is something very important. So before discussing ANOVA, I think it's good to discuss all these proofs up to assignment 3. So unfortunately, we'll not be able to, it's fortunate for you because you will not be able to submit assignment 3 via Cal. Anyway, we will discuss this up to assignment, the proof up to assignment 3 tomorrow. And after discussing the proofs, then we will start discussing about ANOVA, because we need to, you cannot have any doubts when you start ANOVA, because ANOVA is something really, really important in regression. So if you have any questions up to that point, you can ask now. Do y'all understand what I'm saying?
Yes, ma'am.
how about the last week's the assignment session, which was conducted by Miss Pavitra? Did y'all, I think she explained nicely. Did y'all understand all those proofs?
Yes, madam.
Okay, then I'm going to stop today a bit early. I'll stop from this point. So tomorrow we'll start discussing about these proofs. And then on Friday, we can discuss about ANOVA. Okay, so I will upload this today's session to the YouTube, and will share. I will share the link to Sandeep, and she will share it with you all. And the lecture materials also I will mail to Sandeepa. She will share it until we get the access via Cal. So tomorrow Zoom link also I will share it with Sandeepa. So I have to trouble her because the Cal is not working these days. So you'll have more trouble, Sandeepa, during
No,
this
it doesn't matter.
period. Okay, anyway, then we'll stop from this point. Have a nice day.
Thank you, madam.
Yes.